This is an automated approach to modeling Jupiter synchrotron radiation from radio telescope observations. Seen in the image at right, we have Jupiter's magnetosphere. Synchrotron radiation is a phenomenon caused by charged particles, in Jupiter's case, metallic hydrogen, following a curved orbit, usually due to the presence of a magnetic field. Why we should care. In science, it is always our goal to get to the truth, and uncontrolled variables obstruct and clutter what the truth actually is. And thus, eliminating an uncontrolled variable, such as synchrotron radiation in the satellite Juno data, would provide more accurate atmospheric concentrations and water data for the rest of the scientific community. We had two data sources. One was from a private JPL contact that gave us peak temperatures at different dates for Jupiter, and the other was through a public Horizons JPL ephemerides database that gave us the central meridian longitude, facing the longitude of Jupiter that was facing Earth at that time, and the distance. And combining these over the date is what we use for our research.
So there are three main sections to our data processing, namely the noise removal, baseline subtraction, and Gaussian curve fit. So first we remove the noise from the data. We use two thresholds, one for the base and one for the peak. And for each data point, we compared it to the 10 most adjacent points in the scan. Then for the baseline subtraction, to remove the baseline of the noise reduced curve that lay outside the peak was set to a third-degree polynomial, which was sufficient enough for this particular data set. We then subtracted this baseline, which placed almost every measurement that was not a part of the peak near zero. We fit what was left over from the baseline subtraction of each scan to a Gaussian curve, as shown on the next slide. To a Gaussian curve, as shown on the slide. So top left equation is the actual Gaussian fit curve, what we use to fit the scan to the Gaussian curve. And the bottom left is what we used for to determine the half-power width for every curve. These scans were thrown out because they had not very good half-power widths, so which made them produce pretty bad fits and curves.
Yeah, so from the peak intensity, which was that topmost point on each Gaussian fit, we computed this for both Jupiter and each of the calibrator quasars. Then we accessed the flux of the calibrator quasars that were scanned, and then we computed the flux of Jupiter just from this simple ratio relationship that we called lovingly the fundamental theorem of the Magneto-Bremsstrahlung. From the German word. Then we had to scale this flux for distance, for the inverse square law. So we normalized all the measurements to a distance of 4.04 AU. So we had a model of flux at any arbitrary distance. We then plotted this against the central meridian longitude accessed from the ephemerides database, noting which measurements were from each of our calibrators, or which were compared to each of our calibrators. For calibrator 3C353, we had a fairly continuous distribution. For the other calibrator, we had some other problems that we'd like to do more research to resolve. But for the first calibrator, we were able to construct two models of CML versus flux that we could just plug in the longitude and access the flux. The first is a semi-periodic polynomial model with continuous first derivatives at the endpoints. The second is a piecewise trigonometric model that might be more natural for such a phenomenon.
There are multiple conclusions that can be made. This includes automating JPL's procedure for radio telescope scan processing, calculating the flux of Jupiter using a relevant calibrator quasar, and developing a model of central meridian longitude versus flux that can be used to enter a central meridian longitude and get a flux returned.
For future research, a larger data set, greater span of dates, and using different calibrator quasars would all be useful in both improving the fit and finding out more about the unexplained variations in our data. And furthermore, volcanic activity on Io might interfere with Jupiter's magnetic field, which could account for other unexplained variations and fluxes at the same longitude between scan dates.